All right, welcome everyone to today's seminar. Thank you for attending and sorry for the short notice. Today's seminar is going to be given by Dr. John Dorelli. John received his undergraduate degree from Purdue University in 1993, and then his PhD in physics working with Jack Scudder from the University of Iowa in 99. After that, he worked as a postdoc at Los Alamos National Laboratory and is now a member of today's seminar. Thank you for attending and sorry for the short notice.
Oops.
Apologies, I have the stream open in two places and I don't know where the second one is. No, maybe it's gone. Okay, sorry. So moving on. John is now at Goddard as a civil servant, and he'll be continuing, or I guess finishing up our machine learning series from the summer. And he'll be talking about heliophysics applications of physics-informed machine learning. So sorry for the interruption, John, but you can take it away now.
All right. Thank you very much. Thanks, Kyle, for the invitation to speak in this seminar series. And thanks, everybody, for your time. What I'd like to do today is give you an overview of some applications of machine learning and heliophysics, and in particular, what's called physics-informed machine learning. NASA, as we all know now, has taken an interest in promoting machine learning and heliophysics in other areas, and so we benefited from some funding from NASA for some of this work. But in particular, what I'd like to do is call out the Center for Helioanalytics, and this is a group of data scientists at NASA Goddard, and that we've benefited a great deal from interacting with as we're climbing the learning curve on some of this stuff. And so I know a lot of people in the community want to learn more about machine learning, and I would highly recommend contacting the folks at the CFHA to help you get started with that. So the plan for the talk is I'll give a sort of very high level overview of what physics-informed machine learning is, and go over some of the applications. There aren't very many yet, as you might expect, that have appeared in literature, but there are a few. And then I'll go into a little more detail about a particular application we're working on, just so you sort of get an example of how these models are developed and deployed. And that's very much a work in progress, but I think it's useful to present it to this group. So let's see if I can get my, okay. So first of all, why physics-informed machine learning? We're all magnetospheric physicists, and we all understand that we just don't have enough data, spacecraft data, to build models. You know, we're not like the solar physicists that get these nice global images of the sun. We have these spacecraft that are basically like microscopic vehicles. I like to think of it as exploring a living organism. The magnetosphere is very complex system, and it's composed of subsystems. They're equally complex, and those subsystems have their own subsystems, and it's really an enormous range of scales with complexity at every scale. So, you know, I always think of this cheesy movie from the 60s, Fantastic Voyage, where, you know, a group of scientists are shrink-rayed down and they go into this vehicle and enter this human body. And what would it be like to try to understand the workings of the human body from just exploring in one of these microscopic vehicles? That's kind of the situation we're in. And, you know, it's depressing in some ways, but also I think there are lots of opportunities for making progress with some of these new methods. Currently, we focus mostly on physics-based modeling in combination with these sparse spacecraft observations to get a sense of the global picture. But what I'm hoping to convince you is that modern machine learning methods are offering new and very exciting ways of combining physics-based modeling with data. So there have been attempts in the past to incorporate physics and data, combine physics and data. I think the most well-known in our field is what's called Grad-Shafronov reconstruction. And the basic problem is, you know, we have this, you know, this line of spacecraft observations, this time series, this world line of spacecraft observations. And how can we use that information to reconstruct a more global picture of, say, the magnetic field? And so Sonrup et al., way back in the early 2000s, I think maybe even the late 90s, these first appeared, I'm not sure, but used what's called the Grad-Shafronov equation. This equation is basically describing static equilibrium in an MHD plasma. And the neat thing about this is that, if you have this vector potential A, the level curves of that thing are also curves of constant pressure. So if you can measure the pressure on one of these lines, you can sort of treat, the way they do this is they treat this as, some initial data that you can then finite difference step away from that initial line and reconstruct the global structure of this, in this case, a flux transfer event. And this is kind of amazing that you can do that, but when you look at what the content of this equation is saying, it's saying that basically these level curves of A are constant pressure lines. So if you know the pressure, you can kind of extend that knowledge around these level curves of A based on this equation. It's a very strong constraint, actually encodes some global information from a single spacecraft trajectory. The problem is that the way this is usually solved is it's an ill-posed problem. This is what's known as an elliptical partial differential equation. If you kind of treat this as an initial value problem, you might run into problems. And sometimes when you try these reconstructions, you do run into problems, things blow up. The other issue is it can't handle time-dependent structures. So as soon as you start including more complex equations that involve time evolution, then you start to rapidly run out of information from your spacecraft data. And so how, you might ask the question, now we have much more powerful models like neural networks. Can we use that and can we combine those with our physics knowledge to build a more global time-dependent picture of the system? I mean, you can capture very complex structures with neural networks, time dependence, spatial dependence, very high dimensional input. So this is where physics-informed machine learning has really taken off. We have a set of physics equations. The nice thing about magnetospheric physics is we kind of have a good, everybody agrees on what the fundamental equations are. It's really Maxwell's equations, the Vlasov equation in a collisionless plasma. We know what those are. We should be able to leverage that knowledge to build, to enhance our spacecraft data. And so what I'll start with is just this review paper by Karniadakis et al., who was one of the pioneers of the physics-informed machine learning. There's a very nice Nature paper on this from a few years ago. And he talks about several ways that you can introduce physics bias into a machine learning model. The first is kind of the obvious one, observational bias. And this is just the idea that if you have some source of data, and this could be, real observations, or it could be output from some physics-based simulations, where you know what the physics is underlying that data. You just then throw a ton of data at your machine learning model, and then, the physics will sort of, the physics bias will automatically be included, right? You'll learn the distribution that's consistent, distribution of the data that's consistent with the underlying physics. And so, but there are other ways of doing this. I think the second way of introducing bias, inductive bias, this I would say is sort of the holy grail here, because if you can incorporate the physics into the architecture of the model itself, then, in principle, you need very little data to constrain the model for any particular instance of a system, right? And so the classic example of this is a convolutional neural network that builds in, the statistics of natural images just into the architecture itself. It's modeled almost biologically by the way our visual cortex works. And we've evolved over time to be able to really kind of classify different types of natural images. CNNs kind of work in a similar kind of way. It would be nice to sort of generalize this to other kinds of physics equations or physics principles that you could bake into the architecture, so that any kind of image that's generated by the model will automatically satisfy those physical principles. And then the third one that I'll mostly be focusing on today is what's called learning bias. And this is where this is so-called soft constraint, physics constraint in the machine learning model. where you can introduce the physics equations as constraints in the loss function of the model. And so that can sort of nudge the learning process in a direction that's consistent with the underlying physics equations. And so example of observation bias. So, say you have, the advantages of this are we have very mature, well-established models. They run on very big computers. We can generate tons of data. It may be prohibitively expensive to generate enough data to effectively train a very large model. So if you would say wanted to do a three-dimensional time-dependent simulation of a magnetosphere, a planetary magnetosphere, you might need an enormous amount of data, billions of examples maybe to train such a model and make it predictively powerful. That's a disadvantage, but we've been doing these simulations for decades and lots of data already exists. It just may not be, in a publicly available or machine learning ready form. This is an opportunity, I think, for us to, for folks that are interested in kind of making this sort of data available to existing machine learning models. I think that's a wide open problem. We should really be archiving all of this data with the idea that we can eventually use these to train future machine learning models. Examples of baking in physics into the architecture of the model. I'm going to digress a little bit and talk about Gaussian processes, because this is the first place where I kind of discovered that this was being done in a very kind of compelling way. So if you don't know what a Gaussian process is, read this paper, this classic paper by Rasmussen et al., 2006. But essentially what it is you imagine you're plotting a function like on the lower left here, you have a discrete set of points at which you're plotting the values of this function. Well, if you consider the values of the function at these discrete points, the probability, the joint probability of that set of function values is a Gaussian distribution with some mean and some correlation matrix here. This is described as a kernel function. That's what a Gaussian process is. So you're essentially randomly sampling function values at an arbitrary set of points from this joint Gaussian probability distribution. This kernel function is basically describing how well behaved the function is, right? So it's basically telling you how correlated the values of the function at two different points are as a function of the distance between those 2 points, right? So if the function values are highly uncorrelated at nearby points, then you're going to get a very ratty looking function. And if they're very strongly correlated, you're going to get a more smooth function. So this kernel function is really what's kind of giving you the sort of shape of the function. And by tweaking this kernel function, you can create different types of function spaces, if you will. So for example, in this paper from 2017 by Jidling et al., they show how to construct Gaussian processes that automatically satisfy divergenceless constraint. So we know from a Gaussian process, if you take the derivative, if you want to take the derivative of a Gaussian process, you're taking derivatives of the kernel matrix. So if you were to say reconstruct a magnetic field, you could construct a Gaussian process of the vector potential and then take derivatives of that and then get another Gaussian process that is the magnetic field. And that every time you sample a function from that Gaussian process, it automatically satisfies the divergence of b equals 0 constraint. And as you might imagine, that's very powerful because you don't need very much data then to reconstruct a magnetic field. Because you're automatically building in a very powerful physical constraint. So that's, I think, a really great example of building in physics constraints into the architecture itself. So now let's talk about physics-informed neural networks. So I think all of the excitement started with this paper by Raisi et al. In 2019. The idea is very simple. You're effectively saying, hey, can I use a neural network as a PDE solver? And if I give it some initial data, on the left, this left boundary here, time is horizontal, and we have one spatial dimension here in the vertical. and then some boundary conditions along the edges. And then at a bunch of random points inside this domain, we require that the physics equations are satisfied. And then we put those as terms in the loss function of the neural network, and we just treat this as an optimization problem to find the optimal solution that satisfies the initial and boundary conditions. That's really basically the idea. So if you're familiar with so-called collocation methods of solving partial differential equations, it's very similar to that. In a collocation method, you assume some functional form, usually some basis function expansion for the solution of the PDE. Then you plug that into the partial differential equation, you get some residual that you can then try to minimize by varying the coefficients in the expansion. And you can think of a neural network as similar to that. It's like a basis function expansion that adapts to the data. And so that's really basically the idea of physics-informed neural networks. The advantage there is we don't really require a computational mesh or any kind of topology for the points, the collocation points, because all of these neural network packages now allow you to use automatic differentiation to just calculate derivatives exactly at any arbitrary point in the domain. So we can just add that to the loss functions. Any combination of derivatives that we can evaluate exactly in the simulation domain, that can be a constraint in the loss function. The disadvantage, the big disadvantage, and I can't overemphasize this, is that you have to retrain this neural network every time the initial and boundary conditions change. And so it's not finding a general solution to the PDEs. Typically it's very expensive to train these models. Also doesn't scale very well to higher dimensional input. And the reason is simple. You need basically the points at which you're evaluating the partial differential equation have to be more or less uniformly distributed in the domain. So you can imagine if you're increasing the number of dimensions, you're going to run into an exponential increase in the number of collocation points required to train the model. And so, this is the curse of dimensionality really rearing its head again. Neural networks were, one of the great advantages of neural networks is solving that curse of dimensionality, because the architecture of the network can represent complex probability distributions. You don't need to sort of, histogram the entire input space, which is going to give you this exponential scaling in the compute time. But then here it comes back again when you're trying to include PDE constraints. That's not really a solved problem yet in physics-informed neural networks. And later on, I'll talk about some more recent work that's been done to address that issue. But it works pretty well for small-scale simulations, one-dimensional problems. I'll show an example of that for the MHD equations in a moment. So here are a couple of applications that people have worked on. So on the left, this is a paper by Chris Bard and me on trying to use physics-informed neural networks to solve the MHD equations. So on the right, you can see what we're showing here in the horizontal axis is the spatial dimension. And we're looking at the density in this upper right plot. And actually, I think this is, it's the density at a different time, earlier time in the lower right plot. And you can see what the Brio-Wu shock tube is you have a discontinuity at x equals 0.5, and then it kind of spreads out in this system of waves as a function of time. You can actually see that in the left plot, time on the vertical axis, space on the horizontal axis. This initial discontinuity breaks up into a bunch of different waves that propagate away as a function of time. So this is a very complicated dynamic system with lots of structures on multiple scales. And you would imagine that if you just had 4 spacecraft trajectories, these dotted lines here, you'd have a lot of trouble applying something like the Grad-Shafronov approach or some other approach with just 4 spacecraft trajectories. But this physics-informed neural network is able to actually reconstruct the time evolution of this system pretty accurately. I mean, if you look at the black is the exact solution, the red is the reconstruction. If you view this as a partial differential equation solver, it's really not that great. It doesn't really compare to physics-based simulations. But if you view this as a way of reconstructing the space-time evolution of this structure from noisy data, it's actually pretty good. And then on the right here, Enrico Camporeale et al. Show how to use physics-informed neural networks to learn drift and diffusion coefficients of a Fokker-Planck model of the radiation belts. In the purple here, you're seeing phase-space density as a function of time at 2 different L shells. It does actually a pretty good job of comparing with the Van Allen probes. So there's a lot of promise here, but so far, not very many examples of extending this to multiple dimensions, even 2 dimensions, let alone a global 3-dimensional magnetosphere model. So there's still some challenges there. So the example that I'll go into some detail here is a completely different use case, and this is increasing the resolution of a particle instrument. So the particle instrument in question here is the FPI instrument on the MMS spacecraft. And so MMS, as we know, was designed to measure the structure of the electron and ion diffusion regions of reconnection, mainly at the subsolar magnetopause here and in the magnetotail. But it's also been used to make really exciting observations of turbulence in the magnetosheath. And so, as usually is the case, whenever you increase the resolution in a very complex system, you're just going to see more interesting structures, and you would like to increase the resolution beyond your, what you currently have. And that's certainly the case for the magnetosheath. We encounter structures in the magnetosheath that are much smaller than what we were expecting for the reconnection diffusion regions at the magnetopause, for example. And the way MMS addresses this problem is that on the 4 spacecraft, it just puts a lot of electrostatic analyzers around the spacecraft. So we have 16 electrostatic analyzers per spacecraft, 8 electron analyzers and 8 ion analyzers going around the spacecraft. And then so we don't have to rely on a spacecraft spin to recover a high time resolution picture of the distribution function. We're just limited by the time scale of the energy sweep of the instrument. And so here's an illustration of the energy sweep. So and the horizontal axis here is time, vertical axis is energy. The different colors are the different spacecraft. And for each spacecraft, you can see the energy is stepping up and down in this zigzag pattern. And so what we would like is not to even have to not to have to wait for the energy sweep to reconstruct the distribution function. We'd like to be able to fill in these gaps. And so de-alias the particle data, if you will. And so this is just a tailor-made problem for physics-informed learning. Because we all agree that the equation that's satisfied by this distribution function is down here. It's the Vlasov equation. We're measuring the phase-space density F. We're also measuring the electric field and the magnetic field at much higher time resolution than the particles, sort of comparable to the time scale of the energy sweep. So we have much higher time resolution information for the electric and magnetic field. We can use that information and the physics equation itself to try to reconstruct, fill in these gaps with a neural network. So each one of these little circles here in the gaps, we'd like to reconstruct a full image of the sky that satisfies the Vlasov equation. So that's the problem. The way that we do this is we start very simple. We're not doing anything complicated with the neural network. It's just a multi-layer perceptron. The inputs are a velocity vector and a time at each of the 4 spacecraft. So we have 1 neural network per spacecraft that's trying to reconstruct a function of velocity and time. And that function has to be consistent with both the data. So we have this typical mean square error of the reconstruction minus the observations at each of the energy steps. And then we have a physics loss. And so once we have the output of this neural network, we can use automatic differentiation to evaluate all these derivatives, the velocity space derivative, the time derivative. In this initial example, we're assuming that there's no spatial gradient, although there are ways that we can linearize over the 4 spacecraft to include that as a source term in this equation. We're still working on that, but what I'm going to show you is examples of the homogeneous case. And then we had to play some games to ensure that the output of the MLP satisfies some basic physics constraints, like it remains positive because it's a phase-space density. So we accomplished that by putting into this exponential function. And then another thing we did was we include this sigmoid function such that the function vanishes, the overall phase-space density vanishes pretty rapidly above some maximum energy. And this is so that we don't have a whole bunch of zero counts contributing to the data. It's kind of a waste of time to have all these zeros sitting out there when we have no observations really to constrain the model. Okay, and so here's some initial results of that. So what we did was we took an analytic model of the phase-space density, and this is just a plasma with a sinusoidally varying parallel electric field, so that the bulk velocity of the plasma is just sort of sloshing back and forth in response to this parallel electric field that's sinusoidally varying. And it turns out there's an analytic solution for that. It's very nice. We can generate fake data. It looks like this. This is the ground truth data. What we're showing is a spectrogram, which is a function of energy on the vertical axis and time on the horizontal axis. And we can see the phase-space density goes down, then up, and there's an oscillating parallel bulk velocity associated with this parallel electric field. And so our model here, so we're basically training this neural network on a laptop, so a single CPU on a laptop. So initially, just to sort of play around with this and see if it's feasible at all, we use a relatively small neural network. It's a 2-layer MLP. There's 128 hidden units in each layer, so it's about 17,000 parameters. We have about 600,000 or so noisy data samples, and then the same number of randomly chosen collocation points. And so that's basically the model. Here's the output of the model after some number of epochs of training. I think it's 10,000 here. And what you're seeing is that there are artifacts in the reconstruction, but in the regions where the count rates are actually significant, where you actually have signal, the model is actually doing a pretty good job of reconstructing the time variation of the phase-space density, on scales of a millisecond or so, which is about a factor of 30, for the electron instrument, a factor of 30 increase in time resolution for this toy model. And so here's a neat movie showing what the ground truth looks like. Here, vertical axis is energy. This theta here is one of the look directions along the magnetic field. So you can see this thing sloshing back and forth in time as the electric field oscillates on this, several millisecond time scale. If we just reproduce the 30 millisecond DES sky map, what you're seeing is the aliasing effect. So this oscillating parallel current essentially becomes this 2-lobe distribution function, which you're basically turning an oscillating bulk velocity into a temperature anisotropy by doing that. So that's one effect of aliasing here in the particle instrument. And this physics-informed neural network is able to recover the time evolution and effectively de-alias the particle data. Okay, so what about the plasma moments? So what we did is we took that reconstructed model and we used the FPI moments algorithm, the same algorithm that's used to make the level 2 data, to compute the plasma moments. And here we have the density. The true density is in blue here, and the reconstructed density is in orange. And the bulk velocities, three components of the bulk velocities, Vx, Vy, Vz down here. Vz in the direction of the magnetic field is the one that's oscillating back and forth. You see, we do a very good job of reconstructing that. The Vx and Vy are supposed to be zero. We're getting some kind of spurious signal, but it's, 50 kilometers or so, 50, 60 kilometers or so, well within the measurement error, for the moments algorithm that we're using. And so the interesting thing is the density, the moments algorithm itself has some systematic errors that you can see in the blue here in regions where the bulk velocity is low. We're not, we're systematically underestimating the density. Again, this is within the Poisson error though, of the observations. And so I think we're doing a pretty good job of reconstructing the moments for this simple toy problem. Some future work is we need to figure out how to estimate the errors in the reconstruction. The neural network reconstruction isn't just, the error is not just a random error. There are some, if we go back here to the model output, you see there are some systematic artifacts that are appearing here in regions where the count rate is low. Quantifying that is a bit tricky, so we're still thinking about how to best do that. Okay, so now the real question is, it's nice that we have this toy model working. We have a single burst. We can run it, I've trained it on our laptop for single burst. That's encouraging, but we would like to apply this to more than just one burst. We'd like to apply it to the entire MMS FPI data set. The issue is, of course, these models are very expensive to train. So on a typical CPU, it took us about 2 hours to train for a single FPI burst. That's not good. I mean, that's not gonna be feasible. Take us months to just even do a day's worth of bursts. So really, what we need is to run this on some high performance computing resources. We're not Google or Facebook or anything like that. So, we don't have access to thousands and thousands of GPUs readily available. It's really expensive to buy clusters of GPUs now that everybody's using them for machine learning. We actually, for a different project, we recently purchased 8 A100s. That cost about $300,000, which is that's a lot of money. I mean, not everybody's going to do that. Then you have to maintain the infrastructure, and often we aren't going to need continuous use of these things. So this is an example of where we would maybe want to go to cloud computing to be a lot more efficient in our use of high performance compute. Here's where I'm going to give a plug to the Heliophysics Digital Resource Library. That is trying to make cloud computing, among many other things, available to the community. And this is something that's being developed by at NASA Goddard by Brian Thomas is leading that and his team. We've been one of the initial sort of guinea pigs, deploying our model here. And just to do a little math, to get a single GPU on AWS, if it's not one of the, you don't want a cluster of 8 A100s, you can pay about, 50 cents per hour for on-demand access. It takes us about 5 minutes now to de-alias a single burst, which would be about 10 days versus months for a day's worth of FPI bursts. And so the total cost there would be about $120 per burst interval for this on-demand processing. So that's really within the realm of, that's doable and very cheap, much, much cheaper than, buying your own cluster. And so it wasn't, this next slide is going to be for, for code geeks, really, just to kind of show you can't really just take PyTorch and just say device equal CUDA, and then you're going to get a factor of, 100 speed up or something like that. When we first tried this, we actually got a slowdown on the GPU relative to the CPU. And really scratching our heads about that for a while until we discovered this thing called CUDA graphs, which is now available on PyTorch, but was not at all obvious that this thing was available. I think it's a relatively new feature. And this is an example of why I think it's very useful for groups. In this case, it was Facebook collaborating with NVIDIA to get this feature in PyTorch. it's very useful to collaborate with with the folks that really understand the underlying hardware. So we were able to just luckily use this feature that had been recently developed, and then we're able to get more reasonable speed up, GPU speed up relative to the CPU. So that gave us about a 25 times speed up. I'm just going to show a little bit of code to show just how easy this is to do. Essentially what the issue was, if in this training loop, you're constantly launching a kernel, CUDA kernel, to do the same calculation over and over and over again. But every time you do that, you have some overhead where the CPU is launching the kernel. And it turned out, when we did profiling of this, most of the time was spent on that overhead, right? So you weren't really gaining anything from putting the data, doing the calculation on the GPU. With this CUDA graphs, you can just spend a little bit more time launching what's called a graph. And this is basically a definition of a sequence of calculations that you're doing on the GPU that you then want to repeat multiple times. And that gives you a tremendous speed up. You kind of eliminate all of this kernel launching overhead. That seems really kind of obvious that you would want to do that, but it wasn't really kind of built into PyTorch as we were using it at the time. And so it's very simple. I won't go through this, but if you want to look at this later on, it's very simple to do this. Essentially, you capture the graph of the calculation, and then the second step is you just take that graph and replay the calculation multiple times in your training loop. Okay, so remember I said before that with physics-informed neural networks, it's a very powerful way of combining data with physics-based models, but you have to retrain every time you have new initial data and boundary conditions, and that really slows things down. There are other approaches that are being looked at called what's called operator learning, and you can sort of think of that, a pin as learning a mapping from an input vector to an output vector. This is learning a function. A neural network is basically a very complicated function. What you'd really like to do is learn an operator from between function spaces. So if you have some initial condition, you want to learn a mapping from an initial condition to a solution. So presumably, if you had such a model, you could just give it an initial condition as input, it would output the solution. So this paper by Lee et al. Shows how an example of how to do that. It's really interesting that you can reformulate this operator learning using the language of transformers, which is the same architecture that's used in these large language models, generative pre-trained transformers. It's very similar. It's neat to see this kind of association between these two things. So I think this is a very powerful technique that we should be exploring in the future for doing physics-based simulations and then combining data with those physics-based simulations. And stay tuned for that. I think there are a number of groups that are exploring this right now in heliophysics. And so I think that's the end of my talk, and I'm a little bit early, so there's plenty of time for questions.
Thanks, John, for a really cool talk. I have a quick question coming towards the end of your talk, the cloud service and the GPUs you guys bought. So it sounds like AWS is pretty good. And if you've kind of ran the framework that you guys did, where you tease out the bugs first on your laptop and then go to AWS to do the bigger stuff. If you use something like that, is AWS more manageable or more cost? Does it have more cost saving than actually going to your own GPUs now then?
I think the answer is definitely in our case, yes. Because like I said, it was something like 50 cents per hour on demand for the use of a GPU. And if you add up all the bursts, I forget what the exact number is, if we were going to process all of the bursts for MMS FPI, it would be significantly cheaper than purchasing your own cluster. Then you have to have the infrastructure to support that cluster. You have to have a system administrator. Then there's all kinds of NASA rigmarole regulations you have to go through to maintain that, and it's just a lot more expensive than being able to do this on demand. So, the issue, the question really is, how expensive is it going to be for NASA to, provide the community with these kinds of resources? If it becomes really popular and everybody wants to use, AWS, then costs are going to, of course, increase. So I think that's an issue. But certainly for our particular case, it was cost effective for this particular use case to go to AWS.
Yeah. Cool. So a follow-up question. We've chatted before, and I think before this, you were using a different cluster, possibly at one of at Pleiades that had a GPU cluster that NASA was running. Is something like that just hard to maintain in that there are new graphics cards coming out that are faster, have more cores, have larger memory, and so on top of the buying stuff, AWS is also just going to keep you up to date with newer technology?
Yeah, so that's a good question. Certainly there is the issue of your machine becoming obsolete, and we're already running that with our A100s. It's like, wow, we'd like something newer, but you can always kind of swap those out. That's, I think, part of the maintenance and infrastructure and cost of maintaining a machine like that, is keeping it up to date. But the other thing I'll say is that you don't often need, for this application, we were originally thinking, oh, let's just get a cluster of eight A100s, and that's significantly more expensive on AWS than just the T4 that we were using for 50 cents per hour. But we could just get our job done with that older generation GPU quite easily. So you have a whole menu of options with AWS to play around with. Experiment with, without having to sort of go all in and purchase, a particular cluster. So I think that's another reason to where AWS has an advantage here, is being able to not only explore, not only experiment with prototyping models, but hardware as well, optimizing the cost there.
Yeah. So I think we have a follow-on question from John, but I think you partly answered it here. How does the cloud option compare with using a supercomputer that has GPUs on the computer nodes? When I think you kind of touch base with AWS, just have more hardware options than what you'd have with a single.
I think if you had, if you were constantly using the machine to train your model, like you just constantly had new data coming in, and you're having to constantly retrain. I mean, I can see where it makes sense to have a dedicated in-house cluster for something like that. Certainly physics-based simulations, it's really cost effective to do it that way. But when you have this sort of on-demand training and you're not running the machine every day for hours at a time, in days and weeks and months, then it's certainly cost effective. And so for the MMS data set, it's really, all the data. I think Brian Thomas and team have gotten all of the data on AWS in an S3 bucket, the entire data set. So it's living right there next to the compute. It's kind of it's very convenient to use the cloud for that sort of thing.
Cool. So that's all the questions we have today. Thanks again, John, for a really cool talk. Next week, we will have a talk by Cole Dorman, and he will be discussing the development of self-calibrating magneto-inductive sensors for spaceflight constellations. So I hope to see everyone next week. And thanks again, John. Have a wonderful week, everyone.
All right. Thanks, everybody.